In this installment, we're going to summarize Newton's laws of motion and where they came from. And what you will see is that all of Newton's laws are consequences of the law of conservation of momentum. They aren't actually anything truly all that special. They're just consequences of the law of conservation of momentum. So Newton's first law, which we've seen many times in the course so far, is that any body tends or seeks to keep its current velocity, period. That's it. Any body wants to keep its current velocity. Now, there is the more middle school and high school kind of textbook phraseology, which a body in motion tends to stay in motion, body at rest tends to stay at rest unless acted upon by an outside force. That's what every school child will tell you. They may not be able to tell you what it means, because what it means is this: any body wants to keep its current velocity, period. That is the statement of Newton's first law. It is the law of inertia. Bodies resist changes to their motion, whether it is stationary or it is in motion. The only thing that causes a body to change its current velocity is an interaction. Due to one of the fundamental forces. And the fundamental forces that are relevant for bodies that we see are the electromagnetic interaction and the gravitational interaction. And as we will see in the upcoming unit, all other references to forces are really just consequences of electromagnetic interactions of bodies. Bodies interact with each other because of electricity or magnetism or gravity. So unless there's some electromagnetic interaction or gravitational interaction between one body and another, the body will keep its current velocity. Now, Newton's second law basically says that when there is an interaction or change in velocity, it is governed by this equation, which is F net equals ma. The net force is the sum of the forces. So if the sum of the forces interacting on something is 0, the acceleration will be 0. The change in velocity will be 0. But really, this is a consequence of the law of conservation of momentum, which says that force is, by definition, the rate of change in momentum. The difference between two bodies changing their momentum, if we observe them, if they're changing their momentum at the same rate, they're having the same interaction. But if the rates are different, we call that difference in the rate of change in momentum force. So the definition of force is delta P over delta T. Now, how does that lead to Newton's second law? Well, momentum is usually due to a change in velocity. And delta V over delta T is ma. That's Newton's second law. But really, it's about momentum. And by observing rates of change in momentum, we created the concept and the formal definition of what a force is, the rate of change in momentum. Newton's third law says, and we can see this very clearly when we have an explosion type interaction, the law of conservation of momentum, which says the initial momentum equals the momentum at any instant in time. So, if we have two bodies exploding apart from each other, the initial momentum is 0, and so the final momentum must be 0. But we would have, if we have two bodies, momentum 1 and momentum 2, body 1 and body 2, they now have momenta. And for this to be true, the momenta must be equal and opposite to each other. And since they started with an initial momentum, then the delta P of one must be equal and opposite to the change in momentum of the other. And the time during which this interaction occurred is the same for both bodies. The time that one was interacting with two and two was interacting with one were equal to each other. So therefore, that interaction that was causing their momentum to change occurred over the same time interval. Just as two people shaking hands, the time of the shaking hands is the same for person 1 and person 2. It is not possible for one to shake hands with 2 without 2 shaking hands with 1. So the rates of change of momentum are equal and opposite. So Newton's third law says that the delta P over delta T are equal and opposite. And since the rate of change in momentum, rate of change of momentum is the definition of force, then for every force there is an equal and opposite force. When there is one force, there is an equal and opposite force, bringing about the change in momentum. So this, the high school child definition of this, for every action, there is an equal and opposite reaction. Most people don't really understand what that means. It really means for every force, there is an equal and opposite force. Because every force is the result of an interaction. Because the law of conservation dictates that there will be change in momenta for the two bodies involved, the time during which those change in momenta are involved, and since the definition of force is the rate of change in momentum, the changes in momenta of both bodies require that the rates of change in momentum are equal and opposite. Therefore, the forces are equal and opposite. So one can simply think of it, for every force, there's an equal and opposite force.